Right, last time we looked at doing some decimals to fractions using a short, quick method. Sometimes though you are expected to prove these things using some algebra. Now this is fiddly and it requires a few steps. So we might not do all of these, depending on how we go. So, the first one we're going to look at is this one here. We know we're going to get 2/3 at the end, we've done it before, but let's show you the algebraic proof you are sometimes required to do. So the first step in this is just to pick a letter. So let's let n equal 0.6 recurring. So there we are, we've got some algebra set up, and that's the algebra started. What we need to do is get all the recurring digits into our whole integer region above 1, into our units and higher. So here, because there's only one recurring digit, if I multiply by 10, I'll go up the 1 column and I'll have my 1 repeating digit. So 10n is 6-ish. Now this requires you to remember what the 6 recurring is. This 6 recurring is actually the same as 6, 6, 6, 6, 6, 6, 6 forever. This line of 6's never stops. So if I move these all forward a column, how many 6's are still after the decimal place? Well, all of them still, because it never stops. It's infinitely large. So that 6 is there. And it's still repeating, so it's still 6 recurring. So there's an infinite list of 6's here. There's also an infinite list of 6's here. We've now got 1 in front. If I now subtract these, I'll do it the other way up to make it simple. So 10n take n leaves 9 n's behind. 6.6 recurring, take away the 0.6 recurring, leaves 6. And this piece of algebra here has no recurring decimals in now. We've got rid of the recurring problem. Simple algebra now, divide by 9 to solve it, we get 6/9. That fraction simplifies to 2/3, which is what we expected. So the conceptual step here is that when we shift these up columns, we don't lose any at the tail, because that's the nature of the infinite, that it's always there. So let's just do 2 more of these. So we'll skip one of these out and go to this one. So let's let p equal 0.351 all recurring. So, remembering that the useful step here was subtracting off all the recurring parts to get nothing recurring. To get that to line up properly, we're going to want to move all 3 of these up past the decimal point, which means moving left 3 columns, which means multiplying by 1,000. So that gets us 351.351 recurring. And if we do that, we can then subtract them. 1000p take p is 99p. No, it's not. It's 999p. That subtract that is 351. Now we do the simple algebra, some division. And then this fraction simplifies again. It's as tedious as before. And that eventually simplifies down to 111. But you've seen that cancellation before, top and bottom both divide by 9. So general principle here is multiply across by what you need to get the recurring stuff to cancel out and balance up nicely. So, what we're going to try now is the one that's not like the others. So, this 0.012, but they're not all recurring. So we are again going to want to multiply to make sure all the recurring stuff is whole, and that is again 3 columns. So that's going to be 1000x, and that gets us 12.12 recurring. We've got a problem here though, because if we do our subtraction, the 1 isn't lined up with the 1, and the 2 is not lined up with the 2, which means they won't get rid of themselves, they won't cancel out neatly. So if I could just shuffle this across a bit, I could also get this lined up. If I just multiply that by 10, I get 0.12 recurring. So this is x shuffled over by 1 column, and this is x followed by 3 columns. And that means here we've got a nice lining up of our recurring sections. So I can now do the subtraction. 1000x take 10x is 990x. 12.12 recurring, take away 0.12 recurring, just leaves 12 behind. And that simplifies down to x is 12 9/90ths, and we've done that before. That cancels down to 2 115ths. So the cancelling is the same. The answer is the same. You don't, if all you care about is what fraction it is, you never need to do this. However, sometimes you are required to prove this. And if you're asked to prove it, this is the method they expect in the exam. This was a very useful technique back when the infinite recurring decimals, infinite and recurring, was a bit up in the air, but we kind of resolved that bit of math a few centuries ago now. So it's now just a thing you check to see if your algebra is good enough for a proof. If you're feeling excited by the prospect of this, why don't you try this one in your own time, hopefully, and you'll see something that you've heard me mention before but never actually got the proof of. So enjoy that and have fun.